Hi folks, welcome to the 9.2 lecture video, and we're going to talk about separation of variables. Now, in this section, we are going to focus on two main things. The first is to use separation of variables to solve a differential equation, and then the second thing is we're going to solve applications using separation of variables. Okay, so let's go ahead and get started. There's a theorem in mathematics for this separation of variables. And it tells us that if we have a function of y times y prime equals g of x, then what we can do is integrate both sides to solve our equation, okay? But what's really important here, and we'll show this as we're going through the problems, is that we want all things x on one side, and separately, we want all things y on the other side, okay? It doesn't really matter whether the x is on the right side or the left side, but the x's and y's in separation of variables have to be separate, okay? So let's take a look at example number 1. It says, solve the differential equation y prime equals 2xy squared. Now, one of the things I notice here is that all of the terms on the right-hand side are multiplied together, like it's 2 times x times y squared. That's a really good clue that we want to use separation of variables, okay? So when like all the things are multiplied together, that's really what we're able to do is our separation of variables, okay? So let's set this up. I prefer to write my y prime as dy dx, and then I'm going to have my 2x times y squared. And what I'm going to do is I'm going to take this dx and I'm going to go ahead and multiply it to the right-hand side, okay? And at the same time, I'm going to take this y squared and I'm going to divide it to the left-hand side. And so what that gives me is dy over y squared equals 2x dx. Okay, so this is the stage where I would say that I am separating the variables, right? And I'm clumping all the y's and dy's on one side, all the x's and dx's on the other side. Now, before I integrate, I'm actually going to rewrite this left-hand side so that it might look a little bit nicer for the brain, okay? But I'm going to set up to integrate both sides. So I'm going to write this as the integral of 1 over y squared dy, okay? And I'm able to say that because dy over y squared is the same as saying 1 over y squared times dy, okay? And that is going to equal to the integral of 2x dx, all right? So in this step, I've separated and now I'm setting up to integrate the left side. And if I integrate the left side, I also have to integrate the right side, okay? Now, once I am done with this, now I just have to actually integrate, okay? I'm going to write this as the integral of y to the negative 2 dy. And we know that on the right-hand side, the integral of 2x is just x squared plus c, okay? I wanted to rewrite this because this right here will require that we use power rule, okay? So I'm going to get y to the negative 2 plus 1 over negative 2 plus 1 equals x squared plus c, okay? I'm going to simplify this left-hand side, and I get negative 1 over y equals x squared plus c. This right here is what we call an implicit solution. All right, we talked about that earlier in 9.1, how an implicit solution just is like, it's not y equals something yet, right? We would have to do some algebra in order to get it to be y equals. This is just like -1 over y equals x squared plus c, okay? We can turn this into an explicit solution just by solving for y. And I'm going to do that by multiplying the y over to the right-hand side. So I have -1 equals y times x squared plus c. And now I'm going to divide that x squared plus c over to the left-hand side. And I'm going to get y equals -1 over x squared plus c. This is what we would call an explicit solution. Okay, so we have implicit solutions, we have explicit solutions. They're both solutions, just one of them, that explicit one, is just y equals already for us. Okay. Now, some of you may be wondering, well, how come we have a plus c on this side, but like we didn't have a plus c on the y side? So it turns out that we did have a plus c over here, okay? But at the end of the day, what's important is like c is a number. The c on this side is a number. So I could just pretend that I subtracted that c over and I just got one number at the end of the day, okay? So really, when we're writing these, we usually keep the plus c with the x side, but you only need one, okay? All right, let's try example 2. Says, solve the differential equation y prime equals 6x over y squared. Now, I look at this and I see multiplication and I see division and no addition or subtraction. And that's a really good clue that I'm going to be using separation of variables, okay? So I'm going to write this as dy dx equals 6x over y squared. And now I'm going to separate. So I'm going to multiply the dx over, and at the same time, I'm going to multiply this y squared to the left-hand side. And that's going to give me y squared dy equals 6x dx, right? This is our separate step. All right, now after we separate, what do? We integrate, okay? So I'm going to integrate y squared dy, and I'm going to integrate 6x dx. Okay, now both of these sides just require power rule, no use of, no other fancy methods that we learn, just power rule. So on the left-hand side, I get y cubed over 3 equals, let's see, 6x squared over 2 plus c. Okay, now that's not simplified, but this is something that we could consider our implicit solution. Okay, now let's practice finding our explicit solution. So we're going to go ahead and multiply both sides by 3. So y cubed equals 18x squared over 2 plus 3c. Okay, and I can write that as y cubed equals 9x squared plus 3c. And my last step, I just got to get rid of that cube. I'm going to go ahead and take the cube root of both sides. And this will be our explicit solution. Okay, so let me take a look at example 1 and example 2 all on one page. But for both of these, we noticed there was multiplication and division, no subtraction, no addition, just multiplication, division. So we use algebra to separate. And after we separate, then we integrate. And after we integrate, then we decide, okay, this is our implicit, and then we're able to also solve for our explicit solution. Okay? All right, let's take a look at one more example here. So in this case, it says find the particular solution of 1 plus x squared y prime equals 2x y minus 1 that satisfies y of 0 equals 3. So this y of 0 equals 3 means that 0 comma 3 is our initial condition, just like we learned about in 5.3 and 9.1. Okay, what this means is at the end, we're not going to have a plus c, but we're actually going to find a number for that c. Okay, so I know I've been saying no addition, no subtraction, and yet we got a plus and we got a minus. Okay, let me tell you why this is sort of an exception. So I'm going to write this as 1 plus x squared. So this whole thing is times dy dx. And that equals 2x times the whole thing, y minus 1. Okay? So what I'm going to do, I'm going to take this dx and I'm going to multiply it to the right-hand side. And then let's write that out and then let's see what comes next. Okay, so 1 plus x squared dy equals 2x y minus 1 dx. Okay, now I still have some x's and y's on the left, and I have x's and y's on the right. So I still need to separate, like all of my x's need to be on one side and all of my y's need to be on the other. So this 1 plus x squared, since it's times dy, I can actually divide that to the right-hand side. And this y minus 1 is times the 2x and the dx, so I can actually divide that over to the left-hand side. And so what we end up with is 1 over y minus 1 dy equals 2x over 1 plus x squared dx. Okay? This one took a little bit more work to separate, and that's okay. Sometimes we need more than one step to separate, okay? But as long as we have parentheses around the things that are added and subtracted, we can like multiply and divide that whole clump, okay? But once we've separated, now we get to integrate both sides. So integral of 1 over y minus 1 dy equals the integral of 2x over 1 plus x squared dx, okay? Now, in this problem, I intentionally chose this one because I wanted us to know that we have to remember rules beyond just our power rule. And in particular, one rule that's pretty important here is our U sub. Okay, so U sub comes up again and again, but I'm going to actually use U sub on both sides of this. So on the left-hand side, I'm going to let U equal y minus 1, and my du equals just 1 dy. Okay, let's call this u1. On the right-hand side, I'm going to let u2 equal 1 plus x squared, and my du2 is 2x dx. All right, so I'm going to be able to substitute on the left-hand side with a u1 and on the right-hand side with a u2. So let's take the time to make that substitution and see what we get. We end up with the integral of 1 over u1 du1 equals the integral of 1 over u2 du2. Okay, so in both cases, I get just a u in the denominator. Now, when we're integrating 1 over u, or 1 over x, no exponent, just an exponent of 1, this is our special natural log case, okay? Now, if this were, let's see, u cubed on the bottom, we wouldn't use natural log, but it's u to the first power, so we can use that natural log, okay? All right, so now we've integrated both sides. And before we do anything else, let's go ahead and plug back in our y minus 1 and our 1 plus x squared. Okay, so this is going to give me natural log of y minus 1 equals natural log of 1 plus x squared plus c. Now, if I asked you for a general solution, we could stop here. But since we have some initial conditions and we're asked to find a particular solution, we have to plug this 0 and 3 in for our x and y and then find a number for c. Okay, so I've got natural log of 3 minus 1 equals natural log of 1 plus 0 squared. All right, we're going to do a little arithmetic. We get natural log of 2 equals natural log of 1 goes to 0. So c is actually just natural log of 2. Okay. And what that means is that our particular solution is going to be this line, but instead of a c, I'm going to write natural log 2. Okay. So ln of y minus 1 equals ln of 1 plus x squared plus ln of 2. This is our particular solution. Okay, so I hope these 3 examples were helpful. I'm going to come back in part 2 of the video, and we're going to go through 3 examples of applications or word problems when we might need to use these techniques. Okay, I'll see you back here for the second part.